Hello, welcome to this tutorial 1.4, the fourth in a series of tutorials on preoperative cardiopulmonary exercise testing. In tutorial 1.4, we will be consolidating the understanding of identifying the anaerobic threshold, and you'll see I've already drawn the two graphs I left you with at the end of tutorial 1.3. This tutorial and the ones preceding relate to normal responses, and the next couple of tutorials will also be relating to other normal responses. So the anaerobic threshold, we want to identify the point where we get a change in relationship between carbon dioxide output and oxygen consumption. So here's carbon dioxide output on the top graph on the vertical axis, and on the horizontal axis is oxygen consumption. And I've plotted for you in turquoise these sequential readings during a test as the person exerts more power and therefore consumes more oxygen and outputs more carbon dioxide. You'll see that these turquoise dots form a curve, and the default method for identifying the anaerobic threshold is to bring in this solid blue cursor line from the lower right hand point, bring it up to the turquoise dots and leave it touching the turquoise dots, and the last dot to the right that is in contact with that solid unitary tangent indicates where our anaerobic threshold is. So we bring down a vertical line to the oxygen consumption horizontal axis and work out what that value is, which is about 1,600 mils in this particular case per minute. And the second graph that you go to confirm your identification of the anaerobic threshold is this one here, that plots what are called ventilatory equivalents, in this case for oxygen, but you can also plot ventilatory equivalents for carbon dioxide. As the exercise progresses and becomes harder, the person initially breathes deeper, and the proportion of each breath that is dead space falls as you take in bigger and bigger breaths. And plotting that ratio of minute ventilation to oxygen consumption, that ratio gradually falls as the gas exchange becomes more efficient, because your amount of this value, the minute ventilation, the amount of that's actually useful increases as a proportion of the whole VE. So the minute ventilation is going to be composed of dead space, but also physiological space as well. And as the physiological space or volume of that breath increases, this ratio of minute ventilation to oxygen falls. The absolute values of both, so the absolute values of oxygen consumption is going up, and the absolute value of minute ventilation also goes up, but the value of oxygen consumption goes up faster, so this ratio falls. And it keeps on falling to the point where the efficiency of gas exchange for oxygen deteriorates, and it deteriorates because after the anaerobic threshold you are having to breathe extra air to get rid of carbon dioxide that is evolved through non-oxygen mechanisms, so through anaerobic mechanisms. So you're looking for the lowest red dot, and you can see it here, and it's coincident with the anaerobic threshold above. One thing you have to check is that the ventilatory equivalents for carbon dioxide at this point, at the anaerobic threshold, are either falling or have reached a plateau. If your ventilatory equivalents for carbon dioxide also go up at this point, you cannot conclude that that is the anaerobic threshold, because if the carbon dioxide goes up, if the ventilatory equivalents for carbon dioxide go up, then you are also hyperventilating in relation to carbon dioxide, and that does not fulfill the criteria for defining the anaerobic threshold. Okay, so these are your two graphs that you want to look at to identify the anaerobic threshold. So let's get rid of those for the time being and look at just a couple more, well, one other that you can also use. So you see I've left the ventilator equivalent graph there. So the point where gas exchange is most efficient for oxygen, where the ventilator equivalence is lowest, is down here. What that means is when that air you'll then breathe out has had a lot of oxygen sucked out of it. So the partial pressure of oxygen in the exhaled gas will also reach a nadir at a similar point. Then as you hyperventilate in relation to oxygen, it will go up again. The corresponding partial pressure of carbon dioxide in the exhaled air goes up and goes up a bit beyond that to the respiratory compensation point, and then comes down again. So you can just confirm that the anaerobic threshold indicated by the modified V-SOAP method and by the ventilator equivalent method also corresponds to a nadir in the partial pressure of exhaled oxygen. So just here. Okay. Personally, I don't find it a particularly useful graph. The main graphs I use are the modified V-SOAP method backed up by the ventilator equivalent for oxygen. Sometimes you'll need to redraw the ventilator equivalent for oxygen as with a different horizontal axis. So instead of oxygen consumption, which is what I've drawn here, occasionally these dots are very messy and they become a bit clearer if you change the horizontal axis to time. Unfortunately, by doing so, you then cannot align it vertically with the modified V-SOAP method that I drew previously for you. So your default for identifying the anaerobic threshold is the modified V-SOAP method supported by ventilator equivalents, and for both you should have the horizontal axis as oxygen consumption. So what else should we be looking at to determine the normality of a test? Well, one of the graphs that you should go to first of all is a graph of the respiratory exchange ratio. So if you remember, the respiratory exchange ratio equals the carbon dioxide output divided by the oxygen consumption. And in aerobic conditions, this value is less than 1. So the value of 1 has particular significance on this graph. So we're going to graph respiratory exchange ratio during a cardiopulmonary exercise test. So as we've got time, we can plot what's happening during the bicycle ride. So we have a period of rest, 3 minutes of unloaded pedaling, and then about 10 minutes of loaded pedaling where it gets harder and harder. We are interested to check that the patient is not hyperventilating at rest. So during this period here, we would like the values to be below 1. If the values are not below 1, then the person is hyperventilating. When I sit on the bike, despite not feeling particularly stressed, I tend to slightly hyperventilate. with dots maybe up here. You can try and talk the patient down, so to speak, and try and get them to breathe more quietly and not hyperventilate so much. So not such deep breaths, slower, shallower breaths. And by relaxing the patient, these values should come down. And what values should they be when we start the exercise test? They should usually be around about 0.8. They will change even during their aerobic period. Before the anaerobic threshold, they will gradually increase. So what we'd expect to see, let's get rid of those abnormal ones because we're concentrating on normality, aren't we? So what we'd expect to see normally are dots down here. They'll tend to creep up a bit. That is normal. The anaerobic threshold has not been reached yet. And then they'll carry on going up to the end of the test here. Remember, I said that on a previous tutorial that the anaerobic threshold happens before you breach RER equals 1, before the respiratory exchange ratio equals 1. So the anaerobic threshold has to be somewhere in these data points here, somewhere in there. You cannot tell from the graph of the respiratory exchange ratio where the anaerobic threshold is. You cannot tell. So you do need to go back to your modified V-slope method and plotting out the ventilator equivalence for oxygen in order to identify where the anaerobic threshold is. So looking at the RER before you look at other parts of the test will help you to determine the reliability of the measurements. If you've got lots of dots up here, the person was hyperventilating, they're dumping a lot of CO2, which means that your subsequent identification of the anaerobic threshold is messed up because their carbon dioxide reserves in their body have been altered. And that means that the extra CO2 generated during the onset of anaerobic metabolism is obscured. So if you see this in a patient at the beginning of a test, you either want to talk them down to get the RER down, or you may want to start them pedaling. And often when they're no longer thinking about breathing, which they tend not to do once they've started pedaling, these values will also come down without bringing them to the notice of the patient. So in this tutorial 1.4, I've just consolidated the anaerobic threshold identification and introduced the graph of respiratory exchange ratio, which you should refer to determine whether you can reliably identify the anaerobic threshold. In tutorial 1.5, I'll be talking about some other normal responses to exercise that you should be familiar with. And then in subsequent tutorials, we'll look at some abnormalities, some common abnormalities. Thanks for paying attention. I'll see you in 1.5.